Hello, thank you for joining us on this webinar, An Introduction to Optical Measuring Systems. My name is Alan Vitous. I'm a technical sales representative for McCrone Microscopes and Accessories here in Westmont, Illinois. There are a wide variety of attendees here representing a wide variety of companies. I'm sure there's a wide variety of expertise as far as optical measuring goes. If you are an experienced engineer and are familiar with measuring systems, perhaps this might be a useful overview or review of basic principles. If you are new to measuring or perhaps find yourself in a position to have to look at purchasing an optical measuring system, perhaps we can provide you with information that will make your job a little bit easier. Before I go into the measuring webinar, I'd like to talk a little bit about the McCrone Group. It consists of three divisions. The first is our Materials Analysis Division, McCrone Associates. This is an A2LA accredited laboratory, and they provide analysis using applications in light microscopy, electron microscopy, X-ray diffraction, Raman, IR, metallurgy, and many, many other techniques. So if your company has some samples, some specimens, some material that you need assistance with in analysis, McCrone Associates can help you with that. Our next group is the Hooke College of Applied Sciences. This is our education and training division. Hooke College offers courses in polarized light microscopy, electron microscopy, gunshot residue, specimen isolation, preparation, IR microscopy, and many, many other techniques. Course catalog can be seen on our website, www.mcrone.com. Hooke College also partners with North Central College in Naperville and Concordia University in providing a 3+1 program that results in a bachelor's degree in applied microscopy or chemical microscopy. The third division is McCrone Microscopes and Accessories. This is our instrument sales division. We are a preferred dealer for Nikon industrial microscopes and metrology systems. We are a national dealer for the Joule Neoscope benchtop SEM system, preferred national dealers for Lincoln thermal stage systems, exclusive providers for the McCrone micronizing mill, and many, many other laboratory tools and supplies. For more information on any of these three divisions of the McCrone Group, or information as far as how more we can help you, please visit our website, www.mcrone.com, for more information. Now let's get into measuring. If someone presents you with a part and says, I need to know a little bit more information about this part, you have to make a decision as to whether or not you are performing an inspection application or a measurement application. Inspection applications are qualitative. They're subjective. Does this part look correct? Is the surface finish correct? Is the color correct? Do I see any damage or wear? Are the parts fitting together correctly? Do I see any defects? These are inspection techniques, and they are qualitative and subjective when you're looking at the part. On the other hand, you may have to do some measuring. How long is this feature? How large is the hole? Is the hole in the right position? How tall is the feature? What is the angle on this feature? Does it meet the specifications? These are measurement applications. They are quantitative and they are measurable. This is an example of what inspection microscopes look like. These first two here on the left are inverted materials microscopes. The objectives sit here under the stage. You place your specimen here on top of the stage and view them through the eyepieces. You can use a variety of different optical techniques, bright field, dark field, no Marsky, and on many of these you can also mount a camera system. This instrument here is considered an upright materials microscope, looking a little bit more familiar with microscopes that you're used to. Eyepieces are up here, stages here onto which you put your specimen, but the objectives are at the top of the instrument and they look down on your part. You can have two different types of illumination, either reflected light illumination or transmitted light illumination through the part. So if you have a translucent part, a clear part, this would be the type of instrument that you'll be looking at. This is what's called a stereo microscope. It is a rather lower power microscope. It has stereoscopic viewing to give you that 3D inspection aspect. And this particular microscope, as it's configured here on this sheet, does not have a place that you can mount a camera, but many of them do. So all four of these instruments are considered inspection microscopes. They are tools to allow you to determine surface details, features of the part, but are not measuring instruments. Two types of measuring instruments that we are going to concentrate on are profile projectors and toolmakers microscopes, or measuring microscopes. These are examples of profile projectors, or otherwise known as comparators. Some people call them shadowgraphs. You can get up to 500x magnification. They may have 1, 2, or 3 objectives. They usually have a measuring stage of some sort, and they will have a screen onto which the image of the specimen of the part is displayed, as you see here on this instrument. You can have two different types of illumination: transmitted light illumination that comes from beneath the specimen, or reflected light illumination that comes down and shoots light on the surface of the specimen. When light comes up from beneath the specimen, it provides a profile of the part that you're looking at, and this is where you would make your measurements. There are two different configurations of profile projectors. Two of the two here on the left are configured as vertical comparators. Again, you put your specimen here on the stage. You have 3 objectives here that look down onto the specimen, and the image is depicted here on the screen. On a horizontal comparator, the objectives are here at the back and look horizontally across the specimen. And like the others, the image is projected up here on the screen. Many American manufacturers have preferred horizontal comparators because they are much better at handling large, bulky parts, very heavy parts, and because of the heavy industry in the United States, the horizontal comparator has been a preferred instrument for measuring. Measuring microscopes work in a very similar fashion. They have a measuring stage. They have an area where you have either 1 objective or 2 objectives or more. You can mount a camera on the top of the microscope, but instead of a screen, you have eyepieces, either a single eyepiece, as in this instrument, or dual eyepieces, as in this instrument. You can get up to 1000x magnification. You may have a turret with multiple objectives, and of course you can mount a camera on these as well. But how do you choose? How do you make a decision as to whether or not you need to look at a measuring microscope or a comparator? Well, some of the questions you might ask is, how large is my part? X, Y, physically, how large is the part? Or how heavy is my part? You may have a large part, but you're only interested in a very small area. So you have to determine, how large is my area of interest? What is the smallest feature I need to resolve on this instrument, on this part? Am I doing simple measurements or am I doing complex measurements? Is it a simple point-to-point or will there be multiple measurements involved? Am I doing z-axis? Is there a height that I need to measure? Am I going to use eyepieces, or would a screen be more ergonomically efficient for me? If you're using a screen, perhaps you might want to use overlays, which are specific to parts. Do I want to document this part with a camera? What is my throughput? If you are using a comparator with an overlay, that will allow very fast throughput. If you have multiple measurements to do, that slows down your throughput. So all of these questions get into making a decision on what kind of instrument you need, what size, what configuration. There are two different ways that you can do measurements on a comparator or on a toolmaker's microscope. You can either do field of view measurements or you can measure off of the measuring stage. On a comparator, where the image is projected up onto the screen, you can use overlay charts, you can use measuring charts, and many of them also have a protractor screen for measuring angles. On a microscope, you can do field of view measurements using eyepiece reticles. You can use specialty eyepieces such as a filar measuring eyepiece or a protractor eyepiece for measuring angles. And of course, you can mount a camera or software. But on a stage measuring system, you can measure larger parts, parts that are larger than the field of view. You can construct features or relate features that you've measured to each other. You can perform z-axis height measurements, and you can relate the features that you measure to a datum. These are two examples of measuring charts for comparators. The one on the left is a typical toolroom chart. It has a graph on the bottom side that you can use for point-to-point measurements, distance measurements. On the top half of the graph, you have various radiating lines out from the center to show you angles, and you have curved lines that will show you radius diameters if those are important to you. The chart on the right is a specialty chart that you can obtain that shows screw thread pitch dimensions. So if you are measuring thread pitch, you might want a chart like this. You can have custom-made overlays for your comparator that have the profile of your part. On this particular instance, the green line here shows where the proper part would sit, and the dotted lines show both the minimum and the maximum tolerances. These charts are custom-made usually from CAD drawings, and they are calibrated to the screen size and the magnification. You can see how this would be very handy and very quick to put a part on, line it up with this outline, and tell whether or not the part is good. As a go, no-go type of inspection, it's very easy to use for inexperienced inspectors and gives you much faster throughput. The third way that you can do field of view measurements on a comparator is by using a protractor screen. At this sort of instrument, you have a screen with the crosshair, as all comparators do, and you can line one line of that crosshair up to one side of your angle, rotate the crosshairs around to the other leg of the angle, and read off the angle right here on your screen. This can be switchable with either absolute or incremental. You can also switch either degree minute or degree decimal readouts. One thing you do have to remember is the angle that you're measuring does have to be in the field of view, and you want to have the vertex at the center of the screen. On measuring microscopes, or on microscopes of any sort, you can put in eyepiece reticles for field of view measurements. These are very good for simple length measurements. They can be configured in metric or inch specifications. You can have grid patterns, you can have scale patterns, you can have scales on cross lines, or you can have specialty reticles to put into your eyepieces. This one here on the left is a specialty Walton Beckett reticle for asbestos analysis. This one here in the middle is a grain size reticle for metallurgy. You can also obtain specialty eyepieces for your microscope. The top one is called a filar micrometer eyepiece. As you look in the eyepiece, a scale is broadcast over the field of view, and by turning the knob here on the left, you can make a determination of a very precise point-to-point measurement within your field of view. These bottom three eyepieces are protractor eyepieces. The one here on the left actually has a digital readout. So by putting one leg of the crosshair that you would see in the eyepiece, very much the same way that you would do it on a protractor screen on the comparator. You set leg on one angle, one leg of the angle, rotate it around to the other leg, and then you can read off the degree of rotation. These other two eyepieces have manual reading, but you can still do very, very precise readouts of angle measurements. Of course, there's always software. There are cameras and software packages that you can mount on your microscopes. Nikon Elements is a very comprehensive software package that allows you to do point-to-point measurements, circle measurements, z-axis measurements if you have a z-axis scale. But again, you have to keep the part that you are measuring, or the feature that you're measuring, within the field of view. I'd like to talk a little bit about field of view and how the comparator screen size affects the field of view that you have and how it compares to measuring microscopes. Let's take a 10x magnification, for example. On comparators, the magnification of the objective is the total magnification of the system. With a 10x magnification on a 12-inch V12 comparator, you will see that the field of view is about 30 millimeters. If we go up to a 20-inch screen, the 10x will give you 50 millimeters because of the larger screen size. If you look at a measuring microscope, in order to get to 10x, you have to multiply the 1x objective times 10x eyepieces. This combination gives you a 22 millimeter field of view, similar to that of a 12-inch comparator, but much smaller than the 20. If we go up to a 100x objective, again on the 12-inch comparator, you have a 3 millimeter field of view, very similar on a toolmaker's microscope at 2.2 millimeters, but again, not nearly as large as on a 20-inch comparator with a 5 millimeter screen. So you can see that if you need to measure within the field of view, but you have a larger feature that you need to measure, you need a larger screen on your comparator. In general, comparators usually provide lower magnification and higher field of view. Microscopes usually provide higher magnification and better resolution. Now let's talk about stage measuring systems. On these instruments, both comparators and microscopes, you can measure with the XY stage. The XY table has linear or rotary encoders that allow you to determine the distance that the table travels. And as I said before, you can construct features or relate features to other features that you've measured. For the purpose of this webinar, I'm going to only touch on two types of digital readouts. The first series, the Nikon SC series, can be had as either an XY digital readout or an XYZ 3-axis digital readout. The more complicated, or I should say more capable readout system is the Quadracheck system that you see down here. Quadrachecks used to be, you're probably familiar with them, marketed by a company called Metronics. Now they have the Heidenhain name on them. Heidenhain is the parent company of Metronics. The movement of the stage is detected and measured by the encoders on the stage. And remember, in order to do a Z-axis measurement, you need an encoder on the Z-axis of your measuring microscope. This is a very basic overview of the front panel of the Quadracheck. As you can see, you have keys set in different groups to set the mode or the features that you're going to be measuring. When you talk about the mode, you can either set it to measure in millimeters or inches, and you can toggle back and forth. This also allows you to set a datum, and a datum is merely a 0 point on your part. It's usually called out on the blueprint, that allows you to determine where on that part the feature is that you are measuring. You can set the datum, and then by looking at either the XY dimensions, or you can look at the radius and the angle, or radius and angle dimensions, you can tell where your features are that you are measuring. And of course, there is a help key. In order to measure a part, you want to start by establishing the part position on the stage. You'll skew the part, you'll establish the 0 point or the datum, and then you'll measure the feature. In order to skew the part, you will measure or probe on this part, for instance, this bottom line, and this will allow you to set the x-axis of the part to the x-axis of the stage. To establish a datum, you now will probe this side of the part, the y-axis, and construct a point. That point is going to be your datum. You zero the counters at that point, and now every position that you measure on this part will be referenced off of this datum point. You can then look at your blueprint to see if those features are in the right place and if the dimensions make sense. You can measure many different features, probe them. You can probe a point. You can do many points together to form a line. You can determine, is it a circle? You can go point-to-point distances. You can measure angles, and of course you can skew your part. There's also a feature called Measure Magic, which is interesting. You can probe a group of points, and depending on the distribution and the location of these points, Measure Magic will determine whether or not you are measuring a circle or an angle or a line. And of course, the operator can change the feature if Measure Magic gets it wrong. Features that are typically probed are points, or lines, or circles, or point-to-point measurements. Features that are constructed are features like angles, where you have probed two different lines and you want to find the angle between them, or distances between points, between lines, between a line and a circle, things of that nature. You can set in the system whether or not you want to stick with, for instance, a 3-point circle, or if you want to boost it up to 5 points. If you want to determine a line with only 2 points, or 3 points, or 4 points. In general, more points result in higher accuracy of the points of the feature that you are probing. You can also set forward or backward annotation. Forward annotation sets the number of points, whereas backward annotation allows you to probe more points than the minimum number of points required. Some features can be probed. This is an example of probing points on this part to determine an angle. So you would probe along one leg. In other words, you would move the part so that it's under the crosshair, set the crosshair on that edge, and hit enter. Come down to another point on that line and hit enter. Then you'll probe these 2 points. One point on this line here and another point on this line here. Hit enter. When you hit finish, that will give you the angle between these 2 lines. Or you can construct an angle. Here we've taken line number 4 that we've already probed and line number 5 and asked it to determine the angle between the 2. You can also determine whether or not you want to look at the included angle or the angle plus 180, angle minus 180, etc. You can look at individual features. Here, for instance, we've probed a circle, and it looks like they've chosen 8 points to determine a circle. You can, at this point, determine whether or not you want to use a least squares best fit algorithm for determining your circle, or the ISO schema, or if you want to look at the outermost 3 points to determine the circle, or the innermost 3 points to determine the circle. You have those options. You can also construct distances. In here, we've measured 2 circles, circle number 4 and circle number 5, and now we want to find the distance between those 2 circles. Do we want to find the distance between center point to center point? Or do we want to find the distance between the nearest edges? Or do we want to find the distance between the furthest edges? You can construct other features, again, out of features that you've measured previously. This one is called a bolt hole circle. Think of a wheel on your car. You have 5 holes on the wheel for the lug nuts to attach the wheel onto the stems of the hub, and they are centered precisely around a center hole. In this case, we have probed 3 different circles previously, and now we are calling up these 3 circles and making those as 3 points to determine this one larger circle. You can construct or probe intersection points. In here, you have 2 lines, line number 1 and line number 2, and we create point number 3 right here from the intersection of these 2 lines. Remember, this is exactly what we did when we set our datum, our 0 point, on our part. Often these 0 points or datums, or these points that are constructed, they can even be off of the part themselves out in space. I'd like to talk a little bit more about the various profile projectors and measuring microscopes that we offer. The first one is the V12. This is a 12-inch screen and has a stage up to a 10x6 or as small as a 2x2 travel. You can have them with or without a built-in digital readout, and they can be configured with or without the digital protractor screen for measuring angles. This is a benchtop instrument, either has to be on a stand or on a benchtop. This instrument is the horizontal comparator that we referred to earlier. This is the H14LED. This has been just newly redesigned with LED illumination, so it's very bright. It has a 14-inch screen, and I want you to notice that this 14-inch horizontal comparator can hold up to 125 pounds, a very heavy part. Large stages on vertical comparators can hold up to about 44 pounds, smaller stages only about 11 pounds. This one is the V20. This is a 20-inch profile projector. Again, the screen is 20 inches in diameter. It has a turret with 3 objectives, 5x, 10x, 20x, 50x, and 100x objectives are available. And this is a floor standing instrument. There are 3 different varieties of measuring microscopes. This is the smallest one, the MM200. It can be configured in 3 different ways. One with either a monocular eyepiece tube, which we saw originally, or you can have 2 versions with a camera only and no eyepiece. One with a fixed magnification objective and one with a zoom objective. The MM200s come standard with a 2x2 stage, 50 millimeters by 50 millimeters travel. The larger instruments, the MM400 and MM800, again can have various configurations. Both systems can be ordered with or without a Z-axis encoder. Both can be motorized, and both can be configured with either a simple XY digital readout or a Quadracheck. If you look at the configurations, the L systems have the Z-axis micrometers, and the M stands for motorized. Some common features for both the MM400 and 800. They have similar stages, but the MM400 can only go up to a 6x4, whereas the MM800 can go up to a 12x8. Because the MM100 is shorter, is a smaller stage, you have a maximum Z height of 150 millimeters, whereas the MM800 gives you an extra 50 millimeters of height. You can have either monocular or trinocular heads. You can have single or dual objective mountings, and you can also have heads that have what's called a focus aid. If you're familiar with the SLR focusing with the split screen sort of situation, that's what this looks like. It's a split screen where you focus your instrument until the image is clear, and that gives you accurate focusing. This is a screen showing the various stages. It's difficult to read. I don't expect you to read them. But again, this shows you the configuration of stages from the 2x2 all the way up to the 12x8. And depending on, again, the size of the specimen, the area of interest on your specimen that you need to measure, and the instrument that it goes on, that will help you determine which stage you need. There are also many other instruments, measuring instruments that are more sophisticated. We won't go into them on this webinar. There are computer-based systems where you can plug your comparator or toolmaker's microscope into the computer software and do the measurements through the computer. Or you can have more advanced systems like the Nexiv, which is a multi-sensor system. You can have touch probes or video probes, and it's all programmable, CNC programmable. You can have a CNC measuring instrument like the Altera systems. You can do a 3D laser scan investigation of your part. And we even have X-ray applications. That was a brief overview of basic measuring systems. If you have specific questions about any of the systems that we talked about, measuring applications, or if you just need additional information, please contact me on my office phone, 630-734-6473, or drop me an email at avitos@mccrone.com. Thank you very much for attending.